Have you ever heard the comforting idea that nothing can suddenly change because the laws of physics won't allow it? In everyday life, that feels true. An object sits where it's put, a chemical reaction proceeds only if you push it, and the world seems stable. But in the quantum universe, stability is sometimes only a pause. False vacuum decay is one of the most startling examples. A region of space can flip from a metastable false vacuum to a lower energy true vacuum by tunneling, then expand like a bubble until the new state overwhelms the olds. Here's the misconception to kill. People picture a bubble that grows outward through space, like a balloon. In reality, the bubble's expansion is tied to the geometry of space-time itself, and the crucial signature isn't just energy change, but an entropy-like burst, an explosion of disorder in the newly available degrees of freedom. So what exactly decays? How does a region of space tunnel? And why does entropy surge as the bubble expands? To understand the before state, imagine the vacuum not as emptiness, but as the lowest energy configuration of fields. In the Higgs sector, for example, the Higgs field has a potential energy landscape. The bottom of that landscape is the true vacuum, the most stable configuration, but physics may also allow higher, slightly higher energy valleys, local minima. A region trapped there is a false vacuum. Classically, it would stay put because escaping the valley requires climbing a potential barrier. Before any decay, the universe is therefore stuck in a metastable configuration. Like water in a container with a bump, you could theoretically tumble over, except the bump is quantum and the water wave function can leak through. This idea shows up not only in particle physics, but also in early universe cosmology, where phase transitions and inflationary scenarios rely on the behavior of fields sitting in such valleys. The question physicists ask to is simple in words and brutal in practice. If escape is forbidden classically, what mechanism allows it at all? The core mechanism is quantum tunneling applied to spacetime. Think of a ball in a bowl, separated by a hill from a deeper bowl. The ball can't roll over the hill if it lacks energy. But quantum mechanics says the ball's wave function can penetrate the hill and appear on the other side with some probability. In field theory, the ball becomes the field everywhere in space, and the hill becomes the potential barrier between vacua. A false vacuum decay event is described by a special solution to the equations of motion in imaginary time, often called the bounce. The bounce is not a process that unfolds in real time like a movie. Instead, it's a mathematical object whose existence determines a decay rate. Once tunneling creates a critical bubble, large enough that surface tension can't pull it back. The inside of the bubble is in the true vacuum. The outside remains false vacuum. Now the bubble expansion. As the bubble grows beyond critical size, the energy difference between vacua becomes a driving force. The bubble wall behaves like a membrane with tension, and the interior's lower energy acts like a pressure pushing outward. But because this happens in a relativistic setting, the bubble wall accelerates, approaching the speed of light relative to the surrounding false vacuum. This is where geometry matters. In a simplified, flat spacetime picture, the wall sweeps out a hyperboloid. Different observers slice the event differently, but the wall's spacetime trajectory is well defined. For an observer far away, the transition looks like a sudden change after a delay. For an observer moving with the bubble interior, the expansion is an internal expansion of their accessible region. As the true vacuum region forms, the field configuration relaxes, releasing energy into excitations, particles, radiation, and correlated field fluctuations. The entropy burst idea comes from this. The false vacuum had a very constrained set of degrees of freedom, effectively frozen by being trapped in a local minimum. After the transition, those constraints vanish. Many more microscopic configurations become available to the system, and that translates into a rapid increase in entropy, not because of an initial messiness, but because the state now supports a far richer spectrum of excitations. More states open up, so probability spreads across them. The bubble wall also carries energy and non-equilibrium dynamics, and as it interacts with fields around it, it can thermalize or at least scramble information efficiently. In short, the expansion isn't just energy converting to heat, It's the system moving into a regime with vastly more accessible microstates, hence an entropy-like surge. This is why the aftermath can resemble a violent cosmological event even if the underlying transition was rare. How do we know this isn't just a poetic picture? The Suffolk framework computes the decay probability by finding the most likely tunneling configuration, the bounce, and evaluating an action. The resulting decay rate is exponentially suppressed when the barrier is high and wide, which fits the idea that false vacuum decay is unlikely on human timescales, but potentially relevant cosmologically. Early universe models exploit this. If the false vacuum energy dominates, it can drive inflation like expansion, then a decay could end that phase. In more modern views, the question of whether our vacuum is false depends on the standard model parameters and possible high-energy physics beyond it. Small changes in particle masses or interactions can dramatically reshape the Higgs potential at high field values, altering whether a metastable minimum exists and how long we have before tunneling. Remarkably, the same mathematical machinery predicts not only whether decay can happen, but what the bubble looks like in spacetime and how fast it expands. The broader implication is that stability is conditional, not absolute. If our vacuum is metastable, then the universe's future includes rare transitions, possibly with observable consequences in relic signatures, gravitational waves, or modifications to cosmological histories. False vacuum decay reframes energy landscapes as dynamical actors. The laws allow multiple possible ground states, and the universe selects one not by omniscience, but by probability in quantum fields. It also connects to entropy, because transitions between vacua change which degrees of freedom are active and how they distribute. Entropy bursts are therefore not merely thermodynamic afterthoughts, they are fingerprints of how quantum systems unlock new microscopic possibilities. In quantum gravity and cosmology, where space-time geometry itself responds to energy, a decay is not simply chemistry in a box. It's chemistry with space-time as the reaction vessel. So what should you take away? First, a false vacuum is a metastable minimum of a field potential. It can persist for long times because escaping is classically forbidden. Second, quantum tunneling can still create a bubble of the true vacuum, and the existence of the bounce determines the decay rate. Third, once a critical bubble forms, its wall accelerates and expands so rapidly that the transition can be thought of as a reorganization of space-time accessible states. And fourth, the entropy-like burst follows because the interior state opens up far more accessible configurations, releasing energy into excitations and driving rapid scrambling or thermalization. Stability in this picture is a probabilistic event horizon, something that can end abruptly, even if the rules haven't changed. If you want more deep dives into the weird mechanics behind reality, subscribe.